Diffusion, I think, don't quote me on this, but I'm not going to go into great detail. There's a number of slides here, 33 slides, but you're being challenged right now with your take-home double diffusion problems. So I think I'll let this kind of stand on its own. You have enough to wrestle with there, so to hammer you with that again on the 30-30. I have enough testable material, so I'll be honest with you straight up that I'm probably not going to touch upon this. Okay. I guess close all. And then somewhat the same goes with the beginning of this. What I want you to know here is that the oxidation, no I don't, it didn't work before because I don't have administrative privileges. So the oxidation, all I need you to know from the oxidation is what we talked about earlier. That it's that the interface is virgin and that we're probably going to prefer to use the 100 substrate. And so therefore this dry oxidation that we're going to do for the gate dielectric, that's going to be really nice with that nice clean interface. And then if we were to come in with the wet, we're going to be able to do the isolation from one transistor to the other. Yes?
Could you explain why 100 is the best to use for that?
You would have to go through the, calculate from the different zinc blend what the planar densities are. Usually higher order planes like 111s are much, much denser. So that's why when you cleave a diamond and things like that, it's certain directions that it's cleaving along. But the 111 is definitely more dense. But if you just go through the calculation of planar densities, 100, 111, 110, there's even more exotic ones. There's 311s, there's 511s. But 100 is one of the more benign directions.
So that means it can allow for more things to oxidize on it?
No, it's the least density, so therefore it's the least number of, yeah.
Okay.
So, yeah, so this is that idea. Key interface is ultra clean, never having been exposed to the outside world. That's your main takeaway from the oxidation. Okay, then we get into the quantum mechanics. Okay, so like I said, maybe I have you design a, wait, where is it? I guess I don't have it. Particle in a box, you know, sort of. Let's just, yeah, well, let's use this one then. So you have a particle in a box, and what are the wavelengths? You've got a fundamental, you've got a first harmonic, a second harmonic, and so forth. And that you may have done in physics, E&M. But understand that things tunnel, so quantum mechanical tunneling happens if things are atomically thin. And so if I bring two atoms together, understanding that the placement of those atoms is fixed, the direction because of the directionality of the covalent bond, the distance due to the constituents that they are, there's this preferred interatomic spacing, and that will lead to the forbidden energy gap. And the reason there's a variation in energy gaps is because there's a variation in interatomic spacings. So you start off with the idea of the single atom with its 1s, 2s, 2p, 3s. You smush it together. You smush two of these guys together, and they start, the 1s states start to overlap each other. The 2s states start to overlap, and they can't occupy the same quantum number because of what? Huh? Pauli-Exclusion principle? Another gold star. So Pauli-Exclusion principle, and so the splitting here of the energy levels And therefore, one goes up, one goes down, like the nasty earthquake in Indonesia. What was it, 7.5? So I was fortunate to give a lecture in Indonesia many years ago. Very nice place. But the plates, plate tectonics cannot occupy the same volume of space, and the energy levels cannot occupy the same space of energy. So one goes up, one goes down. In this case, there's an anti-bonding bonding. Now, if you imagine that it's Avogadro's mix of them, where I've got n. Let's again. I usually pick on Avogadro. N is Avogadro's number, so that's a very large number, 6.023 times 10 to the 23rd. And so if I smush that all into a centimeter by centimeter by centimeter cube of silicon, I have roughly a mole of silicon in there. And all those energy levels fractionate into these energy bands. So I get a continuum of energy bands in the conduction band and the valence band. And the 2n states for the 2s and the 6n states for the 2p split equally. So I get 4 states in the valence band and 4 states in the conduction band per atom. How many valence electrons do I have with one of these traditional semiconductors? We have 4, right? So, because it's column 4 in the periodic table. And if it's a 3-5, remember that it's kind of an amalgam of a 3 and a 5, so it's really 2 4s, right? Because they kind of split their difference. So I have 4 valence electrons per atom, I have 4 states, so therefore this is nominally filled. Remember the definition of nominal? So it's usually filled. It's usually filled. And unless I perturb it with light, heat, electricity, these outside forces, they're going to stay there and be. So we have the forbidden band gap. Yeah, here's another version of it. And so then what I've always been trying to emphasize is that most of these are lying along this diagonal. So as the lattice constant gets shorter, the interaction gets bigger, and the splitting gets more dramatic, and the band gap blows up. So this is sort of, although Mother Nature will scatter data points, this is kind of linearly varying from inversely of lattice constant and band gap. Right? So this is maybe more dramatic. How did the exam go? Okay, good. So here's the band gaps. This is a function of lattice constant. So now, as you see these other ones being added, you can see that it makes it even more compelling, I would say. Now you're getting into band structure, right? Not to be confused with band diagram, band structure. Band structure is energy versus momentum, where momentum is a vector. Bless you. Well, that reminds me, I need to get my flu shot too. So if one-dimensional atoms are brought close together, there's the splitting. And I'm trying to show that as you're bringing these together, there's going to be certain wave functions. This might be a little more abstract for the exam, but I was trying to drag you through that you got some idea why I did this, because this is a bit too abstract for you maybe at the 30-30 level. But there's going to be certain allowed and disallowed functions, right? I believe you've accepted this principle of a Fourier series expansion of a step function. You've seen this before, right? Okay. So therefore, you know that there's certain periods, certain functions that are going to represent this step function using combinations of sines and cosines. And so my thought pattern in trying to show that preceding this is think of it the same way. There's certain wave functions that are going to support those modes, and there's other certain wave functions that are not going to support those modes. They're going to be suppressed. And that's kind of this. This is like a Fourier series expansion of the crystal diagram, in real space. And then it turns out that these are the allowed wave vectors of that so the real space crystal means that this is the solution of that real space in energy and momentum space. So I know it's probably hard to wrap your head around, energy momentum space, because it's not real, you don't really look at it. But as you start to do the experiments and start to see how these devices and materials respond, you start to accept this more and more. Remember that formalism I said. Quantum mechanics makes no sense the first time you see it. Oh, you're interrupting me. and makes no sense the second time you see it, but at least it's familiar. And then the third time, it maybe starts to absorb. Yes, sorry.
What are those vectors called again?
This is the band structure. So this is showing the difference between a free particle, which can have a continuum of energy states. So E equals P squared over 2m, right? And so it's continuous parabola. But once you map the wave vectors, energy and wave vectors onto the crystal has boundary conditions just like this has boundary conditions. So there's only certain allowed and wave functions that are supported. And so then it fractionates and there's gaps. There's certain modes that are not supported in that superstructure, that crystal lattice. Of course, that's lattice dependent, so it depends whether it's silicon, gallium arsenide, and so that's why they all have the different, I'll come back to this, Lewin, but they all have different, right, they all look different because gallium arsenide crystal is different than a silicon crystal, so therefore the band structure looks a lot different. But now let's focus on another key property that is very testable, and that is the curvature here. So if you deconvolve this, you can determine that the curvature is inversely proportional to the effective mass. And the effective mass allows us to do the calculations. Here's the effective mass. The effective mass, m star, is 1 over the curvature of the EK diagram. And then that allows me, because otherwise I would have to solve this crystal lattice, the motion of particles through this crystal lattice, with all the all the nasty quantum mechanic details. But by using an effective mass, I can hide a lot of the quantum mechanics, and for some simple some simple calculations, I can use an effective mass, and I can do F equals ma, which is just Newtonian mechanics. Now recognize that m star is really unitless, and so you have to multiply by the mass of an electron, and then you get it in grams. So I'm not sure that's always clear there. Remember, like here, these are just unitless, right? And so it's implied that you're multiplying by the by the real mass of an electron, and so it's usually considered as a unitless coefficient. So what's going on here? I'm doing a lot of talking. What's going on here? Yes.
For the direct, it releases a photon when it travels from covalent to the valence band, and
from the conduction band.
First, okay, and then indirect, it gives off heat. It has to go to a trapping area first, right?
Yeah, or a virtual state. Yeah, this is a trap, but like a virtual state. Yeah, it's a two-step process. So emphasize the two-step process. And so it could either release a phonon or accept a phonon. Either way is really, so there's kind of two pathways there. Yeah, exactly. So this is less probable. This is, cause and effect relationship, and this one is kind of happenstance. Yes?
I thought that these were emitting photons and not phonons.
There's both going on.
Okay. Can we go over the difference between a photon and a phonon?
Yes. So here's that virtual state. So I'm not going to call it ET as a trap. It's a virtual state. And so this is the gamma valley. And this is, what do they say? I don't know, this might be L. And so this is phonon. So this is emitted and absorbed. And then this is the, and so then, so here the carrier, the electron, would come to here by either absorbing a phonon, so its energy, so by absorbing a phonon, its energy went up a small amount, right? Or it releases a phonon, releases heat. What's your name? You get Connor. Connor. So as Connor said, I need to learn everybody as much of you as possible. So as Connor said, this is releasing a phonon, so therefore it dropped in energy a small amount. And so then it's coming from this lower state. Now, this is not really a radiative emission. This is not likely to release a photon. The other one is where that's going to release a photon with energy equal to h nu, which is going to equal EC minus EV, right? The difference in the energies. So this is a photon coming off, which is quantized heat, quantized light. I'm getting me confused. And this is heat, this is a phonon, quantized heat. So this is heat, and this is light. So light doesn't really have much momentum, right? But heat has a lot of momentum. Heat has a lot of vibration. Heat is quantized vibration.
Is a phonon basically just a vibration?
Exactly. It's quantized heat, and heat is a vibration.
So is it more of like a mechanical energy, or is it like
Yes.
Okay.
Yeah.
As opposed to electromagnetic?
Yes.
Okay.
Exactly. Yeah. So.
Professor Bridger?
Yes.
So is it always a photon that's emitted in the indirect transition, or a phonon in the indirect and a photon in the direct?
This is more probable.
Okay.
And I mean, it's more probable to do the phonon for indirect, and it's more probable to emit light with a direct, but you can get a mixture of both. I mean, I had a PhD student who all he did was look at the light coming out of these kind of indirect bandgap materials. And so although this is the more probable, there is still some amount of light, and from there we were able to discern what was happening inside the material. But that's the more probable. Sometimes I think when I give the most technically correct answer, sometimes it might be a little confusing. I might be giving a little too much information, but it's generally heat and light are the two. But you can get both. Okay, so yeah, so you can vary these, like as you vary the alloy composition, you can vary the different valleys here, and thereby change it from. So in this particular material, algas, we can convert this from a direct bandgap infrared emitter to a red direct bandgap, and then it becomes indirect. So, I mean, one possible cliche thing for that lab, if we reorganize that lab and have you do an LED, we could have you do a red LED right about here, 35%, which would emit in the red, and we could make it in the shape of a block O if we want to be a little cliche. Okay, so the electrical properties, now moving into the, this is the idea that we've now built this parking garage, as I've always kind of given the analogy, and that the parking garage is the band gap with the density of states. Now we need to see where the carriers go. So this is where we're trying to find parking spaces for them, right? So here we have the holes, here we have the electrons. This is intrinsic, so therefore there's a 1-to-1 ratio. For every hole that came up, there was an electron. And so here's the donors. So it's 0 Kelvin, they're frozen, and at a finite temperature, they've released their temperature, they've released their electrons. And here's the acceptors. Acceptors accept electrons, right, because of the name. So they accept electrons, creating the holes as a consequence. We can put all these different dopants in. Some are preferred, some are not. What are the conditions for a preferred dopant? What are the what do you say are some of the things you would look for an ideal dopant? I don't know if I emphasize this enough. An ideal dopant would be, I would want this to be shallow, and I would want it to be able to, that I can put it in the lattice, right? The diffusion or implantation or epitaxy that I can put it in. Yes?
Like shallow in what way?
Because of KT, the thermal yardstick, because this will ionize. I need it to do this. This is the ionization. I need that distance to be, this energy to be small compared to KT, because I need the donors to donate. This chromium is not going to donate an electron anytime soon. See how deep that is? It's not shallow like these up here. This is deep. That's going to need a lot of energy to release. It's 0.63. Right? That's huge. That's past green. That's starting to get into, that's almost into the yellow, I think. That's a very high energy difference. So that's not going to release and deliver the electron I need. I need shallow donors, I need shallow acceptors. Because this is how they got there. This is how they created the free carriers that I need. Okay, so Fermi-Dirac statistics is just another way of looking at Pauli exclusion principle. And I'm filling up the energy levels. And as I've told you many times, I'm tend to like my good coffee. And so I think this is more representative, turning the Fermi-Dirac on its side. And then it's like a nice coffee cup, and you're filling with some nice, roasted coffee. And you fill it up from the bottom, just like you pour coffee. You fill from the bottom on up until you get to the rim, and you've filled up and you've run out of space to put your carriers. So this is Fermi-Dirac. And if you start to boil it, then some of the coffee goes off in vapor and you create some vacancies, right? And that's all it is. It's just you're heating it up and you're displacing some of the electrons and moving it to higher energy. So now we're starting to get to really get to somewhere real in the devices. We've got our forbidden band gap. We've got the density of states, which you just have to, at this 30-30 level, accept that they exist. the number of states at which I can put carriers. This is like our parking garage, right? No parking on 3rd and 4th floor. Some parking on the 2nd floor, a lot of parking on the 1st floor, some parking on the 5th floor, like 4th, 5th, no, 6th floor, and then a lot of parking up on the 7th floor, right? So here's our Fermi Dirac, our coffee cup. We're about halfway up, so therefore we got an equal number of electrons and holes. So this is extrinsic or intrinsic? Intrinsic. So intrinsic is no intentional impurities. Extrinsic is intentionally doped. Charge neutrality equation. So therefore, and here's the Fermi level, probability of occupancy of 50%. And so you fill it up with electron, it becomes electron rich. If it's doped with N-type donors, it becomes hole rich. If you fill it up with the acceptors. And then this is what I really care about, right? These are a means to an end. This is telling me where the Fermi Dirac goes up and down based on the carrier statistics. The density of states actually doesn't change. If you notice, this is the same, right? This is the same semiconductor, right? I haven't changed the semiconductor. So if you notice, this is the same. These two are the same as this and this. The only thing that's shifting is the Fermi Dirac, because that's been depending upon the doping. So this is intrinsic, this is N-type, this is P-type, and the electron becomes electron rich if it's N-type. So negative, N for N, N for negative, so it becomes very electron rich. P-type for positive, so it becomes very hole rich, right? But because of the charge neutrality equation, it's becoming hole rich at the expense of the electrons, right? So that we're going to later, as we get into device physics, this will become the majority carrier and this is the minority carrier. And that's the end of that. And what else do we have?